Okay, so we're looking at similar solids. This is what we worked on yesterday in class. I apologize, I'm home with a ill little boy, so is life of a mother. Anyway, we're going to be looking at similar solids. So when we looked at similarity, we did a couple of things yesterday. I think there's only one class we didn't get to. I think Mr. Draper was doing his proof, and we kind of ran over at probably fifth period. But anyway, we have similar solids here. So what we have to do is determine if these guys are similar. Now, if you remember what similar means, similar actually means that they are the same shape. Not necessarily the same size, but the same shape. So similar means they are the same shape, okay? Remember we talked about congruent, meaning same size, same shape? Well, similar is same shape. So talk about dilations. When things expand and contract, when things get smaller, they get larger. They have to maintain the integrity of the shape, which means that when you have a photograph and you smile all big for mom and dad and you take your school photo, your school photograph, you're going to get an 8x10, you'll get wallets for grandma, you'll get 5x7s for your boo and everybody. So all of those pictures look like you and they look proportional. If they did not enlarge those proportionally, meaning doing the same type of enlargement for ratio-wise for all the sides, the bases, and the height of those rectangles, you would look weird. It's kind of like going to a carnival in a fun house and you're looking at those mirrors where they make you look really thin or really short and really wide. Those convex mirrors that kind of mess with your shape. But anyway, so that's what we're looking at here. I want to determine, are these two the same shape? So basically, did I increase this one or decrease, depending on whether, like number 2, it gets smaller. Did I increase or decrease it the same ratio all the way around? Is it the same exact shape? Is it like a miniature or a blown up version? So let's look at number 1. Number 1. Now, first of all, let's look at a scale factor, okay? Down here, I'm going to write it. Scale factor, and I'll use a different color because I'm just that kind of person. A scale factor, I'll try to write it here. The scale factor is what did we multiply the original by to get to the second one. So remember the scale factor, we talked about this a while back, sometime in the first semester and a little bit in the second semester when we did similarity. The scale factor is going to be the image, which is your new shape, divided by the original. So the scale factor is the image divided by the original, and we call the scale factor K. You'll see the word K. K is kind of like a constant, but we call the scale factor K. So let's look at the first one. I'm going to try to determine what my scale factor is. So I'm going to look at these two boxes. This is your image, and this is your original. That's your image and that's your original. So the scale factor is image divided by original. So let's look at the first one, 40. I got to 40, but where did I start? 12. Okay. Let's look at the second one. The second dimension changed to 80 from 24. And the third dimension changed from 260 from 18. So the first question is going to be, are these guys similar? Are they the same shape? Well, if they're the same shape, that means that these changes were proportional, and it means that they all change the same amount. So let's reduce these. If I reduce 40 over 12, I get 10 over 3, because 40, the common factor here being 4. There's 10 4s in 40 and 3 4s in 12. Let's look at 80 over 24, okay? If I want to reduce this, the common factor is actually, the GCF is 8. So this reduces to 10 over 3 as well. So far, so good. We've got the same scale factor. So the thing we got to do is run the last test. 60 over 18. And the common factor with these guys is 6. And that reduces to 10 over 3. So the answer is yes. They are similar. They're the same shape. The same change was made to each side to get the new figure. They are proportional. So what you're going to say is yes, they're similar figures. Now what I wanted you to do additionally is to determine how the volume changed. But we'll get to that in just a second. Let's do one more example. So I'm going to look at these solids that I have, and I'm going to try to determine, all right, well, are these similar? Well, you're going to do the same thing. You're going to find a ratio and see if those were changed proportionally. If they were changed proportionally. And when you have solids like this and you want to know if they're changed proportionally or not, you have to have how many dimensions? 3 dimensions, right? 3 dimensions. So we have to have base, height, and length, or length, width, and height, or base, width, and length. There's 3 different dimensions. It depends on what you're looking at. Sometimes we get them mixed up because when we talk about the area of a rectangle, we talk about base times height. And then we talk about, and when we talk about the areas here with the, when we're doing the volumes of prisms and things like that, we do area of the base. And it's hard, especially with a rectangular prism, you get the bases mixed up, which is base, which is the base of the prism, and which is the base of the figure. So during volume, we usually use length, width, and height because that's the way I want to do it. So anyway, we're just trying to determine if these figures are similar. So we need 3 dimensions for a 3-dimensional solid to determine if they are similar. Now, the question is, how can you determine if they're similar if I only have 2 of these dimensions listed? So for example, look at the next one. I've got 8 that changed from 40. Oh, and by the way, your scale factor is 10/3 for the first one. And I have 20 that changed from 50. So I have 8 that changed from 40. Remember, the new one goes on top. And I have 20 that changed from 50. So the question is, what is my next dimension? How do I do this with something like this? Well, look at the base. That's 50. That's going to be 20, right? Because they're all marked congruent, right? So that'll be 50, and that'll be 20. So what does that tell you? The entire base went from 50 to 20. So are all the bases going to be from, the 3rd dimension is from 50 to 20, just like the rest of them. So let's compare these. Obviously, these are going to be the same. I've got 2/5 here, and I'll use a different color just because that kind of person. I've got 2/5. I've got 2/5 because the greatest common factor here is 10. Greatest common factor is 10. The greatest common factor here is what? 8, right? 8. How many 8s go into 8? 1. How many 8s go into 40? 5. Uh-oh. What do you notice here? This is not a proportional change. This one does not fit with the other 2, so these are not similar. They're not similar. That was a pretty good uh-oh, wasn't it? They're not similar. They're not similar because they don't match. You went from 40 to 8 and 50 to 20. Going from 50 to 20, that's a change of 2/5. Going from 40 to 8, that's a change of 1/5. So those don't match, therefore they are not similar. So that's the idea that you're going to use for the similar solids for the surface area, or when you're looking at area. Now,